This is the video for exercise 7 in chapter 13, but this exercise involves modifying some code from exercise 4 of chapter 12. So that has two implications. The first implication is that before working on this exercise, it would behoove you to go back to this exercise here, 12.4, read through the instructions again, see if you can remember what your answer was there and what you thought of that question. The second implication is that it's actually better to solve this exercise by going back to adjust the code from chapter 12 instead of writing new code here. And the reason for that is that it's not only about the code for this particular exercise, but you also need to recreate all of these other variables. You need to import the Korean bike share dataset. You need to create the design matrix. You need to create the modified design matrix that has that extra column, which was a linear combination of the first two columns, temperature and rainfall. And I'm making sure I remember all this as well. That was where we were studying collinearity and the effects of regularization on collinearity and model fit to the data. Okay, so now what you want to do is redo that exercise. So redo exercise 12.4, but instead of using the squared Frobenius norm, or the Frobenius norm, you want to use the average of the eigenvalues to regularize the matrix. So the average of the eigenvalues is called shrinkage regularization. And actually, I have to admit, the way that I implemented it in code is not literally exactly shrinkage regularization. I'll show you what that means in the code. I will actually show you what the real shrinkage regularization is. But that's not the important part here. The important part is just to work with those data, go back to the code, and change the regularization method so that instead of using the Frobenius norm, you are using the average of the eigenvalues. And remember, these eigenvalues are coming from the design matrix transpose times the design matrix. So the gram matrix coming from the design matrix. Okay, and then you want to compare the results here from chapter 12. Okay, so now I will switch to Python and we'll have a nice little discussion about this. So here we are. You can see this is the code for chapter 12. Now, if you're having trouble getting through the code here from when you're working in chapter 13, you might need to go back and rerun a bunch of code. So you need to rerun the code from the chapter that imports the data set from online, the Korean bike share data set, and converts it to pandas, creates the design matrix. You will also need to rerun the code from exercise 3 here, because that's where we create the reduced rank design matrix with that extra column. So that's probably the trickiest part of this exercise, is just getting it to run. Once you've figured that out, the rest of it isn't that difficult. So I added this toggle here. You might remember this from the video in chapter 12. So previously, it looked like this. It was false because we are not reading chapter 13. Right now, we are working with chapter 13, so we set this toggle to be true. And what implication does that have? So that has this implication here. We run this piece of code here. So you can see here I define lambda according to the squared norm. Here I'm defining lambda according to the average of the eigenvalues. So I take the design matrix transpose times itself, so also called the gram matrix, and then I extract all the eigenvalues here. Note here we don't care about the eigenvectors. We only care about the eigenvalues. And in particular, I'm averaging over all of the eigenvalues of the matrix. Now, this gamma term, that's exactly the same as what we had in chapter 12. Everything else is exactly the same. All the other code is exactly the same. You can see here for the multi-collinearity model, this is the design matrix that had a reduced rank. It's exactly the same thing. The code is exactly the same. You have to be mindful, that you have the correct variable. So this should be desmat m, and up here it's just desmat. So this is the regular design matrix. This is the multi-collinearity design matrix. Otherwise, you just run the code, and then you get this result here. And what you can see over here, this was the result from using the Frobenius norm from the previous chapter, and now here we have the result using the shrinkage regularization. Okay, so you can see that they are both kind of similar in the sense that they both involve shifting the matrix by an increasing amount as we go to the right on the x-axis. And in both cases, that decreases the fit of the model to the data as indexed by the R-squared fit between the predicted data and the observed data. So there are some similarities between these different methods, but you can also see that shrinkage regularization actually involves decaying quite a bit slower compared to using the Frobenius norm. So here we got, really sharp decrease of a model fit to the data for increasing regularization. And here this was much more gradual. Okay, so this is called shrinkage regularization. There is a whole theory about shrinkage regularization and why it's called shrinkage regularization and what impact shrinkage regularization has. Now, I mentioned that what I write here is not literally exactly shrinkage regularization. If you wanted this to be literally exactly shrinkage regularization, it would need to look something like this. So you take the X transpose X, so the design matrix transpose times itself, and you actually have to scale this down by 1 minus gamma, and then this part is the same. So here we are multiplying gamma times something, and here it's 1 minus gamma times something. And the idea is that this is really transitioning from using the design matrix to using the identity matrix. So imagine what would happen if you set gamma to be 1. If you set gamma to be 1, this term becomes 0, which means the design matrix basically completely drops out, right? I mean, this is not the design matrix, this is the identity matrix times times some scalar that is in the scale of the design matrix, but still we end up fitting the model to a identity matrix or a diagonal matrix. And so this, I think, nicely highlights why you don't want this gamma parameter to be so large. You want it to be relatively close to 0. Okay, so as you go throughout your adventures in the land of machine learning and statistics and data science, you will learn more about these kinds of regularizations, how to pick these parameters, and so on. But just in terms of the mathematics and implementation, I hope you found this exercise to be informative.